Welcome to the triggering demo. In this demo I'm going to go through some of the triggering that the CS548 does. This applies to all of our products, but I'm using this with the CS548 and our standard application. We're just showing one channel at the moment, the others have been turned off. We have two signal sources and they're mixed together so that we can make different looking signals to trigger on. On the bottom is a waveform that comes from an external signal generator, and I can vary the frequency and width of the pulses. This is the bottom. On the top we have this internal signal generator. If I set it off, you can see it's off, and I can vary the duty cycle like this, and I can vary the frequency down here, but I'm just going to vary the duty cycle because that's what I'm going to use later for our measurements. To begin with, we'll just have a look at how you actually set the trigger level. You have two ways. You can select a trigger tool like this. That's a rising trigger tool, and this one's a falling trigger tool. So you'll notice that we have a little trigger symbol, and we can trigger there, for example, or trigger there. And if we look at the 0 point, we can look on the tracking display. You can see the 0 point is where the trigger happens, and if we change the trigger direction, it goes the other way. So now we're triggering on the rising edge. We just set the level like this, and we can drag it as well. As well as that, we can just set the trigger level by typing it in. If I can make this 400 millivolts, for example, it won't trigger. If I set it to 200 millivolts, it triggers. Just for argument's sake, let's trigger on the bottom part of the waveform down here. That'll do, and we're making a falling edge trigger. You can see it here. Now we can modify the way we trigger. One of the ways is that we can use a digital pattern. You'll notice I've got digital inputs here, and if I flip some switches you can see the pattern change. Here we have an opportunity to use the digital pattern. If I click that, now it requires digital input 1 to be high before it triggers. I can make up a pattern that's the way I want it to be. For example, I could have this pattern here. So at the moment it's not triggering because I don't have the pattern. So I've made the pattern and now it triggers. There's some switch bounce in the one I'm using. You can see it switching there. If I go and set this to single and do the switch, you can see the transition there as we go from 0 to 1 on the switch. So this is useful if you have some state information and you only want to capture when the state is in a particular scenario. For example, you're looking at a digital system that's got some outputs like an SPI, for example, and you want to trigger only when the address lines are set to a value. You can make sure that you'll only trigger when these address lines match up. Now I'm going to look at some of the other trigger facilities. First of all, just to make it a bit clearer, I'm going to stop the top signal generator from doing anything. So we're just looking at the bottom one here now. The first thing I'm going to examine are the variety of trigger methods. We have two triggers, in fact. This is trigger 1 here, and over here we have trigger 2. You can display trigger 2 by clicking on trigger 2. Trigger 2 has some help, that round button with a question mark in it, and you can see from the help that we have a variety of different ways of triggering based on the time period between trigger 1 and trigger 2, and also on counting trigger 1s or trigger 2s. These are described here, and we're going to use some of those. Let's start by setting up a couple of triggers. So we have trigger 1, as you can see in the tracking graph, it's going low there, and we can use trigger 1 inverted as an automatic method of looking at pulses and triggering on them being too short, too long, or in just the right range. What I'm going to do is look at this pulse here, and if we measure that pulse at the moment, you can see it is about 8 microseconds wide, and I can vary it like this. Now, just for argument's sake, I'm going to zoom in so we only look at one pulse, and you can see here that it's just one pulse that we're looking at. Let's say we only wanted to trigger if the pulse was less than 40 microseconds wide. So what we do is we go in here and set the minimum to 40 microseconds, and we use, let's say for argument's sake, that we only want to trigger if the pulse is shorter than the minimum value. This might be a glitch, for example. The minimum value can be anything down to 10 nanoseconds. So trigger 1 to 2 is less than minimum value. So we go and type the value in here. Let's use 40 microseconds. And we change this, trigger 1 to trigger 2 is less than minimum. Right, at the moment it's triggering. Now if I increase the time, it stops triggering, and if you look over here at the pulse length, we can see that as we come down it triggers, and as we go up and I'll very slowly go past the 40, it stops triggering. There it triggered at 40 microseconds. So anything less than min and we will trigger, and we're doing this over a single pulse. Next one that we can do is we can trigger if the time between the triggers is in a range. So let's make this range 40 microseconds to 60 microseconds and put it in the range. And now it's not triggering because it's too short, so we'll extend it. So now it's from 40, it stops triggering, 60, stops triggering again, so it's just in the range. Next one is if we can trigger only if the trigger 1 to 2 is greater than the maximum. So we'll leave our maximum at 60 microseconds and we'll make it greater than the maximum. And at the moment it's not triggering because it's actually 50 microseconds. So we'll go above 60 microseconds and we'll keep going until it disappears, and it's still triggering. So it triggers because it never sees the rising edge, the opposite rising edge, the one we want here in that trigger time, or if it's less than this, it triggers until we get down to 60. Now it doesn't trigger. Now it triggers. It's not triggering. So we can detect, for example, a pulse that never completes, or look for something that hasn't happened properly. We've been using trigger 1 inverted. Trigger 1 inverted actually means that trigger 2 is set up to be just the inverse of trigger 1, but we can do it ourselves. So if I go trigger 2 definition, I can see that it's triggering at the moment, and it'll actually keep triggering continuously because we have the trigger 2 level set to 200 millivolts up here, and so it never triggers with trigger 2, and so it always exceeds the 60 microseconds. But if I come and make this minus 200 millivolts, for example, it's still triggering because it's more than 60 microseconds. And then if I go below the 60 microseconds, it stops triggering. It starts triggering again when I go above. Now there's no need to just use the digital signal. We can use analog ones as well. Well, let's say linear ones. I'll change to this, blow it up a little bit to see what's going on. It's very noisy at the moment. That's because the signal generator we're using has got lots of internal noise from the local radio stations. So if I go settings, acquisition settings, you can see that I have some filters. I'll just use a 10 megahertz filter and I'll turn it on. Now it's nice and clean. Let's change the slope. I've just made the triggering not use time, and we can see a full slope here, which we can vary like this. Now in some situations we might be interested in triggering on a slope. For example, we might have a switching edge in a power converter and we want to check to see if any of the switching edges are too slow. Or we might have a gate drive and we want to see if it takes too long to transfer charge into the gate. So we can trigger on slope. Let's place a couple of markers that we're going to use to calculate our slope. So I've made marker 1 and it's minus 266 millivolts, and I can make channel A trigger 2 the marker 1 slope, which is minus 156. Now I can trigger just the same way as before, and I can trigger if at those amplitudes being shorter or longer than a particular period, we can trigger off it. So let's make this a range. So now the slope is too slow and I'm not triggering. Slope's fine, I'm triggering. Slope's too fast and I'm not triggering. So we can do exactly the same as before. We can choose to be in a range or below or above. So let's go above. So now we're triggering on a slope that's too shallow. This could be that power electronics switch that's turning on too slowly. There it's off, there it's on. So being able to use analog values on the same edge to trigger allows us to trigger on slopes. Right, I've gone back to the square wave display that we had before and got rid of the digital so we don't have to worry about them. Now we've got this waveform that we can change the duty cycle on. If we add some of that other waveform like this, we can see that the two pulses are not aligned with each other. The question is, can we trigger only when the pulses are aligned? Let's do a bit of work on that. First of all, let's only trigger when the high going pulse is high. So let's change that to 200 millivolts. Okay, so now we're triggering on the high going pulse. I can make it a little bit narrower. Right, and I would like to trigger when the bottom pulse is close to the top pulse, and the simplest way of doing that is to use channel B, and we can stay with our minus 200 millivolts rising edge and set this to a range. Now we are only triggering when this pulse is within a range of this pulse. It could be a useful thing, and when we look at it we can see that we get these steps, and perhaps we would only want to be able to trigger on that step there. So let's for example say the step is 0.15 volts. So that's 150 millivolts, and we're falling edge, and let's make it quite short. So we'll make this 5 microseconds and trigger less, and now we only trigger when that occurs. Now we're going to look at some of the other triggering, the counting triggers. I've actually moved the two channels so that now channel A is the one that we can change like this, and channel B is the SIGGEN here, and my plan is to do some triggering on counts. So channel A, let's trigger on the falling edge as we are doing right now, but we have, if we go and look at this again, with this other option which is to count triggers. So we could, for example, count trigger 2s on trigger after trigger 1's happened. So let's try that. So we'll make up a trigger 2, which is channel B this time, and it's rising through 0. And let's put a number in there. Let's make it 5. And we will use count trigger 2s. Let's just stop it so we can see what we've got. So trigger, there's the trigger point there. So this is supposed to start it. That's 1, 2, 3, 4, 5. We've got 5. So that's pretty good. So if we make that 6, let's just move this across just a smidgen. If we make this 6, we should see that pulse move left by 1, and it does. And 7. So this is quite a useful tool if you're trying to look at, for example, SPI. This could be the chip select, and these could be the data lines. And you might want to trigger on a particular byte value, say the 7th byte value, that's 7 8s are 56. So you could trigger on the 56th pulse, and therefore you'd be looking at the 7th byte. We can combine a time delay with a count. So we might want to do this only when the time between, let's turn this off again, when the time between the falling edge here and the rising edge here is in a particular range. And this means that we only trigger when we have a coherent signal. It's not as though we are seeing a negative falling edge on trigger A, and then some time later, many times, much time later, we start counting pulses. Just to check this out, we can see here, if I place 2 markers, that the time difference here is about 38 microseconds. So what I could do is say, okay, we'll only count if the period is, say, less than 40 microseconds. And trigger 1 to trigger 2 is less than the minimum value, and then count trigger 2. Let's try that. See, we see occasional ones, not as often. If we make this a bit narrower, make that say 20 microseconds, and look at this gap here. We can see it's less than 20 microseconds, and if we make it even smaller, like 1 microsecond, it's not going to happen very often, I would think. There we go. So we can check that the signals are coherent before we start counting them, and there are quite a few situations where this is useful. For example, if you're looking at video signals and you want to look at a particular point in a video signal, you can do it this way, looking at the horizontal and the vertical retrace values. Okay, so that's a fairly comprehensive view of the whole triggering system. Once you start thinking about it, you can actually trigger on an awful lot of things. Thanks for watching.